This video will provide a derivation of the relativistic Doppler equation. And the motivation for this is that when we do satellite work, we rely heavily on the Doppler effect. So it'll be interesting to see what the equations say and then how actually that applies to the frequencies that we get to enter in our transceiver to actually make sure that we are able to sync up to the satellite. So as with anything dealing with special relativity, we start with two frames of reference. Picture this frame right here as an astronaut in space, and this frame of reference here as what we would observe here on Earth in an experiment. Now, our astronaut in space is going to go ahead and shoot a light beam off of a mirror and back. So the time that the astronaut is going to measure is delta t0. And of course, the cavity or the two mirrors that we're looking at are spaced a distance d. So the light is traveling twice that distance d, so its displacement is 2d. That same experiment seen from the Earth is not going to see an up and down motion like the astronaut sees. We're actually going to see, since the spaceship is traversing our horizon, we're actually going to see a diagonal S start from this point, hit some boundary, and come back to the original point, another distance S. So we're going to see these diagonals, and the spacing between one and the other is still d. And so therefore, the time that we're going to actually, or the distance we're going to actually traverse is 2s. Okay? So writing that down is delta t0 for the astronaut is 2d divided by c. And similarly, in our lab frame of reference, we're going to measure delta t, and it's going to be 2s divided by c, where s brings in the diagonals. We can say something more about s in terms of the geometry of the problem. We notice that it's actually a right-angled triangle if we go and say from here to here to here to here, we get this triangle with the hypotenuse being s, one side d, and this other side l. If we say that side is l, then of course our original base of the experiment was going to have to be 2l. But no matter, we call it l. And we notice that also, when we think about it a little bit, that is equal to v times delta t divided by 2, because that is the length, and the time is divided by 2 because we're only looking at half of the trajectory. Keeping on now, we apply the Pythagorean theorem to this triangle. We end up with the hypotenuse equaling to the two sides squared summed together. Once we take square roots, we can then see that that becomes s equals to the square root of that term right there. And remember, this is that l term right here squared. We can further now say, once we put this term s up into this part, this equation, the one that we started out with over here for the change in time, we can express this now in terms of time. So we do that, and we see that s comes in as delta t, and then that's a 2 over c, which comes from up here, times the square root term. Now we then go ahead and get rid of the square root by squaring both sides. We end up with delta t quantity squared equals to 4 divided by c squared times that term without the square root. Now at this point, we notice something interesting, and that is that once we multiply out, we end up with the following. We end up with this term right here, which then we notice is going back to the astronaut's frame of mind in terms of delta t0. It's 2d over c squared. So then we can go ahead and now express not only our equation in terms of delta t, but also in terms of delta t0. So we do that, and we can go ahead and write down the following equation. Okay, here we see the previous equation just cleaned up a little bit, where we use delta t0, the delta t that we had there in the previous equation written out, and that then simplifies to putting all the delta t's on the left-hand side and all the delta t zeros on this side. So we see that v squared over c squared term comes over to the other side, to the left-hand side of the equation. That becomes 1 minus v over c quantity squared times this delta t quantity squared. Once we have that, we can go ahead and divide by this quantity in the brackets, and now we have delta t quantity squared in terms of delta t0 quantity squared divided by this. Therefore, we can then say delta t, by taking the square roots on both sides, delta t equals to delta t0 divided by 1 minus v over c quantity squared square root. Notice that this term right here is seen often in special relativity, and it's actually given a name. This 1 over the square root is defined as gamma. So delta t then can be expressed as gamma times delta t0. Or, in terms of frequencies, and we get frequencies, remember, by inverting both sides. 1 over delta t is, just from units, you can see seconds becomes 1 over seconds, or hertz, which is a unit of frequency, a measurement for frequency. So nu, or frequency, equals to this term now, 1 over gamma, times nu 0. The original frequency is changed due to relativistic effects. So we can actually call it exactly that. This is the frequency correction due to special relativity. Now, let's concentrate on the other effect that we have, which is the Doppler effect. For that, we consider our waveform traveling in space, or let's say with a stationary object, not in motion. And then over here, we have the same wave, but now it's actually being compressed as the emitting tower or signal generator is approaching us. Think of the analogy, of course, of the train heading towards you, and you start hearing the high pitch of the horn. So then that frequency becomes smaller, becomes c delta t1, but now you have this extra term here due to the velocity of the approaching train or the approaching wavefront, which is v times delta t, the delta t being the one at the very beginning from the original one. So now we can write this down to get a little bit of insight. Becomes c delta t equals to c delta t1, which is this quantity, which you can see is smaller than the original one, plus this d, which is v delta t. Now we can go ahead and isolate our delta t1 terms on the left-hand side. C delta t1 equals to the difference of c and v times delta t. Or we can say then that delta t1 equals to, by dividing by c minus v divided by c times delta t, or 1 minus v over c delta t. So finally then what we end up with is another term similar to the one we just had, and this is the frequency correction due to the Doppler effect. And this nu 1, just because we had those subscripts as 1, equals to 1 over 1 minus v over c times nu being the frequency. So again, the two effects that we have are the frequency correction due to special relativity and the frequency correction due to the Doppler effect. We can combine these two, and that's what we do in the next step, because we have nu here, which we can plug into here. We plug into here. And then we have nu 1, or nu measured, equals to the relativistic component and the Doppler component. So let's see what that looks like. Okay, so this one is, again, the only thing we've done is we've just gone ahead and plugged in, one equation into the other. This is the relativistic Doppler effect equation. And that's interesting that we've actually done that, and we can actually see the relativistic component in the numerator and the Doppler effect component in the denominator. The interesting thing to notice is that we have two main cases to look at. For our purposes, we have case 1, the satellite approaches our radio station. This is the acquisition of signal, because over here where the pen is pointing is where our radio station is at, and we're seeing the satellite first coming over the horizon, acquisition of signal. The angle is going to be very shallow. Let's call it 0. Why? Because with the theta, that's the angle, equals just about to 0, that implies the cosine of theta is just about 1. which is going to be useful for us. Case 2, of course, is when the satellite leaves our radio station behind. And that's the satellite over there flying off into the horizon into loss of signal. Again, our radio station is here. You notice that the angle now between us and them, between the horizon and the direct line to the satellite is 180 degrees. And in that case, when theta equals to 180, cosine of theta equals to -1. And so let's go ahead and consider the case 1, satellite approaches our station, and we can then write the following. In this case, our equation becomes 1 minus, and all we've done here is just substituted v cosine theta for v in the equation above, and that becomes 1. So it actually looks a lot like our equation here because cosine theta goes to 1. So the equation that we derive for the approaching of the satellite is pretty much the same equation over here. The interesting thing happens when we look at the second equation. Second equation, remember, had cosine theta equals to -1. And the second equation, case 2 actually, is the same equation. It's when the satellite was pulling away. In that case, we had v cosine of theta, which is -1, but that term is squared, so that's inconsequential. However, the term in the denominator is not inconsequential because we have cosine of theta equals to -1. That -1 then multiplies times the negative here and gives us a plus. So we have an addition taking place in the denominator. So that's something to note. Next, what we're going to do is we're going to look at numbers. Let's go ahead and look at actual numbers from real life. So what we have first of all is the velocity of the traversing space station. V, in this case, in our equations, is 7.6 kilometers a second for the ISS. It's a low Earth orbit satellite, and it goes at 7.6 times 10 to the 3 meters per second. We're prepping that already to have a consistent unit set. C, the velocity of light, of course, is 3 times 10 to the 8th meters per second. So here we see that the speed that we're talking about here for the space station is not going to be relativistic. I mean, that's a factor of 10 to the 5, 0.00001 or something like that. So either way, we go ahead and compute V over C. We get that number, just that number divided by that. V over C squared, that number squared. And again, we're noticing the relativistic term is not going to be consequential. It's 10 to the -10, even though it's going to go underneath a radical. Plugging in here, we end up with, there's our 6.42 term in here. There's our 2.53 subtracted term here. And we end up with the frequency nu equals to the original frequency times 1.0000253. It might seem like a very small number, and it is. But remember, we're dealing with megahertz and kilohertz. So our frequency then looks like this. Specifically for the downlink frequency, remember we have to set our dial to 437,800 kilohertz. But we're told that there's going to be a 10K shift that we should compensate for on the downlink. That's exactly where it comes from. That equation right there gives us frequency 437,811 kilohertz if the original frequency, nu 0, is 437,800 kilohertz. That's our 10 kilohertz shift on the downlink. Similarly, but we're careful about the uplink, because here we're looking at it from the satellite's perspective, and he's going to measure 180 degrees. Remember, that's where the -1 comes in. So the equation, remember, adds this plus down here. So then once we do that, we can compute for the uplink frequency the following. We have essentially that frequency is going to be 145,986 kilohertz if the frequency 0 is 145,990 kilohertz, which is what we need to uplink to the space station. So there's the 3 kilohertz shift on uplink. Now, some folks may say that, the more important, and they're right, I mean, the more important shift is on the 70 centimeter band. because you see it here, it's a 10 kilohertz shift that comes out of the equations. Whereas in the 2 meter band, which we're using for uplink to the ISS, it's only a 3K hertz shift. Either way, that's where these two numbers come from that we're asked to go ahead and put to adjust our frequencies in for our satellite passes. You can work out similar numbers as the satellite recedes, but that actually concludes this presentation. We've derived from first principles not only the Doppler shift equation, but also the relativistic shift equation, and found out that the relativistic shift is not really necessary because of the magnitudes of the velocities involved. But this is where these two numbers come from. We plugged in some numbers and actually got the actual values that we're being told to plug in to compensate. So hopefully that was useful.